Shall we start, sir?
Sure.
Okay. Namaskar and a very good morning to all. Hope I am audible to all. My name is Kalpana Adhikari from Committee for International Commission on Large Dams, India, INCOLD. On behalf of INCOLD, we extend a hearty welcome and sincere gratitude to our President INCOLD, Shri D.K. Sharma, today's resource speaker, Dr. Martin V. Lan, and all the participants for attending virtual workshop. Let me introduce our President INCOLD. Shri D.K. Sharma, presently Honorable Chairman, Himachal Pradesh Electricity Regulatory Commission, has more than 40 years of experience in energy and water resources sector in India and abroad. He worked as Chairman BBMB and Managing Director of HPPCL. He has experience of working in the corporate sector in India and also in Tala Hydroelectric Project Authority in Bhutan. He has worked in SJVNN and in HPSEBL in various capacities. Presently, he is Vice President in International Commission on Large Dam ICOL and President INCOL. He has presented number of papers at international and national level. Now we invite Shri D.K. Sharma for the opening remarks. Over to you, sir. Thank you.
Kalpana, I'd just like to add, sir. Sharma Sahib is a person who has got experience of working in state sector, central sector, private sector. He has been in planning, construction, design, maintenance, in all aspects of civil engineering he has seen. All along, he has been a technocrat, a non-technocrat, but today, he is performing the duty of a justice, being chairman of Regulatory Commission. So, sir, was up to you, sir.
Thank you, sir. It has been really long introduction. Thank you so much, and Patel sir.
हाँ इसको देखना पड़ेगा
कर लीजिए फिर दोबारा कॉल कर लीजिए हम आ जाएंगे देख लेंगे
Can I request to the participant kindly mute their mic? All the participants, please.
Well, I take this opportunity to welcome you all to this workshop on seismic aspects of dam designs. Before I say something, let me congratulate everybody here in India on achieving 1 billion vaccination doses for coronavirus. So it's really great historical moment and prime moment for all of us. So congratulations to all the participants and everybody here in India. Like coming to this virtual workshop on seismic aspects of dam designs, and also I understand Professor Wieland would be covering about reservoir triggered seismicity also. As you are well aware, safety of dams and their potential risks to the downstream region, particularly in seismic active areas, are serious concern to the governments, dam owners, and affected communities on the downstream areas. The complexity in design of dams increases when specific considerations is to be given to seismic forces. There has been rapid advances in technology in the sphere of seismic design practices. Seismic design criteria and methods of dynamic analysis of dams have undergone substantial change since 1930s, when earthquake actions have been introduced to the design of dams. Today, we have clear concept for seismic design criteria to be applied when a dam is subjected to ground shaking, and methods of dynamic analysis have been developed which allow the calculation of inelastic seismic response of embankment and concrete dams. There's need to create awareness amongst engineers, scientists, dam professionals, contractors about the procedures in working out appropriate seismic design parameters utilizing state-of-the technology practices followed globally. In this effort, Indian Committee on Large Dams and the Central Board of Irrigation and Power proposed to hold the workshop on seismic aspects of dam designs. The following topics will be deliberated in the workshop: basic structural designs, single degree of freedom oscillator, seismic design and performance criteria for large storage dams, application of pseudostatic sliding stability analysis in seismic design and safety evaluation of dams, seismic design aspects of low level outlets, spillways, penstocks, electromechanical equipment, seismic design and safety criteria for tailing dams, a comparison with water storage dams, design, construction and seismic safety evaluation, 249-meter high Drnayar Arc Dam in Turkey, reservoir triggered seismicity. So these are the topics which would be covered. And as you are aware, we also talked about the first lecture in this series was held on 14th of October, and this is the second lecture which we are having today. This workshop is being organized with a view to facilitate exchange of views, ideas with professionals at international level on recent advances, current practices, and application of innovative methodologies and new technologies in seismic design of dams, which may help to the professionals for future projects. Well, I'm also to tell you that INCOLD, Indian National Committee on Large Dams, has also brought out guidelines on a seismic design of dams in the year 2008, and these guidelines are being revised by the publication committee constituted under the chairmanship of Dr. R.K. Gupta, Member Design and Research, Central Water Commission. Ladies and gentlemen, let me tell you about the speaker who would be talking to you. He is the best authority when it comes to seismic designs in the entire world. Globally, he is the best person for the seismic design aspects. Dr. Martin Wieland, who is today's resource speaker, has been chairman of the Committee on Seismic Aspects of Dam Designs of the International Commission on Large Dams since 1999. He was also the chairman of Earthquake Committee of the Swiss Dam Society. He is a senior dam and earthquake expert at Poiri, Switzerland Limited in Zurich, where he has been involved in seismic safety evaluation of some of the world's largest dams and other major infrastructure projects. From 1980 to 1990, he was faculty member of the Division of Structural Engineering and Construction at the Asian Institute of Technology in Bangkok, Thailand. He obtained his MSc and PhD in civil engineering from Swiss Federal Institute of Technology, Zurich, in 1971 and 1978 respectively. He is faculty member of ETH. He was faculty member at ETH, which is Swiss Federal Institute of Technology, from 1978 to 1980, and was the first earthquake engineer in Switzerland. He was member of the Structural Advisory Board of Panama Canal Authorities. Shiplock for new Panama Canal recently completed. Has been a member of panel of experts for 230-meter high Karun 4 and 203-meter high Dez Arch Dam in Iran. He has received honorary professorship from Ohio University in Nanjing, China in 2002. He is a visiting professor at China Three Gorges University in Yichang and a distinguished adjunct professor at the Asian Institute of Technology in Thailand. He has authored about 30 technical papers in the field of dam and earthquake engineering, has worked on dam and other infrastructure projects in 34 countries. So we cannot find a resource person better than Dr. Martin Wieland. So now, ladies and gentlemen, I hand over to Dr. Martin Wieland. Thank you. Dr. Wieland, please.
So you are on mute. Kindly unmute your mic, please.
Okay, thank you. Okay, thank you, Mr. Sharma, for your very kind introduction. And I would like to start right now. Okay, it was already mentioned at the beginning, and I would like to give once more an overview. This is a workshop number 2 of the virtual training course of InCold, and I'm discussing here seismic aspects of dam design, which are basically also a prerequisite for the topic on dams and reservoirs, which have been mentioned. So it is like a two-part workshops. Let me say workshop 2 and workshop 3, which deal with seismic aspects of dam design and reservoir-triggered seismicity. I would like to give once more an overview on the online training course. We had already a month ago, we discussed earthquake and dam safety. I discussed modern dam safety concepts to be used for infrastructure projects with large damage potential. Today and tomorrow, I would like to talk about seismic aspects of dam design. Then in November, I would like to talk about reservoirs and seismicity. Maybe here there could be some change in a date which would be announced, as this is also the time which I just recently realized of the eigen annual meeting. So we may make here some small change. Number 4 is a seismic safety of existing dams, will be in December. And the last one will talk about multiple hazards caused by strong earthquakes to dams and appurtenant structures and to other infrastructure projects. So that is the overview. Now, as I mentioned already last time, ICOLD has published a number of bulletins which are related to seismic aspects of dam design. And I have presented them also last month, and today basically we would like to discuss, let me say, bulletin 148, selecting seismic parameters for large dams, because which discusses design criteria, and design criteria are basically, let me say, the input which is required for the analysis. So I will also talk about bulletin 52, earthquake analysis procedures for dams. Is basically linear analysis, this bulletin, but I will talk about dynamic stability analysis here. Then next month, I will talk about reservoirs and seismicity and neotectonics and dams, which are directly related to the seismic hazard. And to understand these issues better, I have changed, therefore, the sequence to talk first about the design criteria and the analysis. So that is the overview with respect to bulletins which have been prepared by my committee on seismic aspects of dam design during the last years. The presentations of a workshop have already been mentioned. I have provided PDF files of the PowerPoint presentations, and the participants should be able to get copies of these PDFs. The first subject I would like to discuss here is already related to some analysis. I will say something about basic structural dynamics. Secondly, I will talk about seismic design and performance criteria for large storage dams. Number 3, I would like to talk about the application of a pseudostatic sliding stability analysis. And number 4, I would like to talk about seismic design aspects of low-level outlets, spillways, penstocks, and electromechanical equipment. And number 5, we'll talk about seismic design criteria for tailings dams and to make a comparison with water storage dams. Tailings dams are quite important because up to now, more people have been killed by the seismic failure of tailings dams than for water storage dams. And the last subjects are related to design, construction, and seismic safety evaluation of the 249 meters high Deriner arch dam in Turkey, which was recently completed. And I will give one more case tomorrow afternoon if time is available. So that is the overview of today's presentations. And I would like to start right away first to give some, let me say, it is not a lecture on structural dynamics, but I will just to give some very basic ideas on structural dynamics. And I hope with this more or less qualitative discussion, it should be possible for you to make an assessment of the importance of dynamic actions on different types of structures. So let me start here. The basic here in any dynamics is in structural dynamics is.
Excuse me, sir. So sorry to interrupt you, but your presentation is not visible.
Presentation is not visible.
Yeah.
Yeah, that's true. I thought it is a problem only with us. Dr. Wieland, your like it is the joint conversation is coming. So I understand you have to minimize it and then go to the presentation.
Okay, we'll just try once more. Do you see the slide?
No, sir. Your browser.
Not so far.
It is not visible. What's the problem here? Used exactly the same as last time.
Please use the yellow button on the top to minimize your screen and then go to open your presentation. Maybe your presentation is already opened.
Now okay, I will delete that once more. Okay.
So just click on the open share tree button.
Yeah, I have just put that, but it.
Yeah, just open your presentation.
Yeah, now it's okay. You go to, please open the relevant file.
give control.
No, it's fine for us. Just open your presentation, sir.
Yes. I was wondering why it didn't work.
Now you can go to. Yep.
Is it okay?
Yeah, now it's perfect, sir.
Thank you.
Okay, so somehow it was, yes. Okay, thanks. So I just skipped here. I want to go once more what I've just said. There are 5 presentations which I've mentioned. I will talk about the presentation number 2 today and tomorrow on seismic aspects of dam design. This presentation today is related basically to 2 bulletins. This is bulletin number 148, selecting seismic parameters for large dams. It deals with design criteria, and I will also discuss earthquake analysis methods, which is related basically to bulletin number 52. The presentations I've mentioned already, and Mr. Sharma has also mentioned them already. It is there are 6 subjects. Maybe I will add one more tomorrow afternoon. And the PDFs of these presentations have been sent to Incold, and you should be able to get copies of these PDFs. So let me now start with this subject on structural dynamics, and I would like to talk about single degree of freedom oscillators, because I hope within a few minutes I can give you an overview on structural dynamics and how you can interpret the importance of dynamic effects in structures. Of course, this is not a course on structural dynamics, which will take many hours. So I try here really to condense and to focus on the most important aspects. I hope you see that. This is what I'm showing here is a single degree of freedom oscillator, which is a mass here attached to a spring with a stiffness K, and we have some damping, which is represented by this icon here, which is represented by the damping coefficient. We have this, the mass of a single degree of freedom system is M, and if this is a mass which is on roller, if we apply some load here, a dynamic load, P of D, it will move here in this direction. The direction here is given as U. The coordinate of a displacement, relative displacement, is U. Now the equation of motion, what I discuss here is now a load. P of T is assumed to be a harmonic load. That means is a P naught times sinus of omega bar T, where omega bar is the excitation frequency. That means the frequency with which we excite this single degree of freedom oscillator. This is omega bar is a frequency in the radians per second, but usually we are more familiar with the frequency in hertz, which is called, which I call here F, is the excitation frequency divided by 2 pi. So that is the frequency in hertz, which is usually the term used in practice. Now, the equation of motion is as follows for the single degree of freedom oscillator: mass times acceleration plus damping ratio times velocity. We assume usually viscous damping. Viscous damping means the damping force is proportional to the velocity, and we have the stiffness term K times U, which comes from this term here. and this must be equal to the applied load P naught times sinus omega t. Now, the dynamic response can be explained. I must say here is something is a little overwritten. Dynamic response is d times the static displacement. Static displacement is if a load P naught here would be applied statically. If this load is applied statically, we have no velocity, so the equilibrium is P naught is K times U static, so therefore U static is P naught divided by K, and the dynamic response, sorry, here it is just overwritten. Somehow, probably I think on your slide it should be okay. The dynamic response is U static times dynamic amplification factor. This is a factor which I'm explaining in the subsequent part. The eigenfrequency of this single degree of freedom oscillator is omega square is equal stiffness divided by m. Okay, that is the eigenfrequency of this single degree of freedom system, which is different, let me say, from the excitation frequency, which I mentioned here. This is an externally applied load. And the damping ratio is defined as Xi is C, the damping, viscous damping coefficient divided times 2 times mass times the eigenfrequency of this single degree of freedom oscillator. And the quantity we have is the frequency ratio F. This is one which I mentioned here, divided by the eigenfrequency of the single degree of freedom system, which is F is equal omega divided by 2 pi also. In the following one, I'm using this frequency ratio. We can say this is a ratio of the excitation frequency divided by the eigenfrequency of our structure. I must say I should go here quick back because this here is somehow up, unfortunately. So okay, that is what I mentioned here. Dynamic response amplitude, the maximum dynamic response is equal static displacement, static response multiplied by the dynamic amplification factor. I hope you can see that. Okay, so this is, let me say, some basic characteristics of single degree of freedom oscillators, and we say the dynamic characteristics of any structural systems are eigenfrequencies and the damping ratio. These are the dynamic characteristics of a problem. The static characteristic of a structure is basically the stiffness. But in dynamics, we have the eigenfrequency and the damping ratio. If we talk about dynamic characteristics, we always talk about eigenfrequency and damping ratio. Now, if we look into different types of structures, I have given here some examples. We have here, for example, an arch dam, or we have here a big roof from a conference hall, or we have a bridge here, a big bridge. And it is possible, I'm not discussing it here in a first approximation, to characterize the dynamic response, to approximate, let me say, the dynamic response of these quite difficult structures here by a so-called generalized single degree of freedom oscillator. In this generalized single degree of freedom oscillator, we basically have the two characteristics which I just mentioned here. We can characterize this dynamic behavior again by the eigenfrequency, but usually here for this complicated structure, we use the lowest eigenfrequency, and the damping behavior is described by the damping ratio. So also for complicated structures, it is possible to simplify the dynamic response by a single degree of freedom oscillator. So therefore, the understanding of a single degree of freedom oscillator is very useful also to help to understand the dynamic behavior of much more complicated structures, which are basically multi-degree of freedom systems. But we focus here on the lowest eigenfrequency, which is often the dominant frequency in our structures. So let me not discuss this further. We will do here a lot of dynamic, let me say, analysis to show how we can model these damps by a single degree of freedom oscillator. This is basically being done in structural dynamics by a so-called mode superposition method, where we consider only the first mode of vibration. So now if we look at this dynamic amplification factor, I must say this is quite an important diagram which helps you if you use that, if you have that in mind. It helps you to qualitatively discuss almost every dynamic problems of linear elastic structure. Okay, what do we have here? In a vertical scale, we have the so-called dynamic amplification factor, which I have mentioned, which is a function of the dynamic characteristics of a single degree of freedom oscillator. It is shown here. On the horizontal axis, we have the frequency ratio. The frequency ratio is omega bar divided by omega. That means is the ratio of the excitation frequency divided by the eigenfrequency of a structure. And we see here, if the excitation frequency, now this is under the assumption that we have a periodic loading, a harmonic loading with the frequency omega bar. So if the frequency ratio, excitation frequency, that means the frequency of the applied load divided by the eigenfrequency is 1, we have what we call resonance. If a structure is undamped, the dynamic response, the dynamic amplification factor, as you can see it goes to infinity. Okay, that would be, of course, only for an undamped system. But in all our structures, we have damping. And if we look how this dynamic amplification factor looks like with the inclusion of damping, with here a damping ratio of 0.2, which represents 20%, 50%, 70% damping, we can see this infinite peak, it decreases. So I would like to use, let me say, this kind of curve for the further discussion. Usually for structures, for concrete dams, we assume damping ratios. In Switzerland, we allow damping ratios only for the safety checks of 5%. In some other places, people use maybe for gravity dams 7% or sometimes even 10%. But in Switzerland, for our dams, the government basically, to be on the safe side, they specify that you should only use 5% damping. So let me now use this diagram to discuss some cases. I mentioned here, as you can see here, if the frequency ratio, excitation frequency divided by eigenfrequency is very small, that means if we have a very low frequency of our structure, of the applied load, if we have a large eigenfrequency of a structure, we have values close to 1. So therefore, we can say in this case, the dynamic amplification factor is basically 1. That means the maximum dynamic response is basically equal to a static response. If D is equal 1, if I go back here, we see here U max, maximum dynamic response, is equal static response times the dynamic amplification factor. And if the dynamic amplification factor, which I've shown, is basically 1, the dynamic response is equal to the static response. Okay, that is what we see in this range. If we are in this range here, that means if, for example, the eigenfrequency of a structure, if the the cursor doesn't want to appear, if the eigenfrequency is very small and we have a fixed excitation frequency, we will get a very large factor. Okay, now it comes. We are in this range. And we see here, if we have a very low eigenfrequency of our structure, the dynamic magnification factor becomes very small. So that means the dynamic response, if I go back here, dynamic response here becomes very small. So the maximum dynamic response is the static response multiplied by a small factor. So the maximum dynamic response is much smaller than the static response if the dynamic amplification factor is small, which is the case for very low eigenfrequency. Now, what does that mean for structure? If we use, I'm sure you have heard about base isolation. If you do a structure on base isolation, basically we will provide an eigenfrequency which is very small. So therefore, base isolation, we are in this range, and therefore the dynamic response, relative dynamic response of our structure is almost 0. So therefore, base isolation is very effective. On the other hand, I must say we can do the opposite. If we make a structure very stiff, that means the eigenfrequency becomes very large. So therefore, the frequency ratio is in this range, and we are in this case. So therefore, the maximum dynamic response is equal to the static response. So for controlling dynamic effects, we can basically make we have two options. Option number 1 is high tuning. That means we make a structure stiffer, very stiff. So therefore, the dynamic effects will be very small. And the other case is if we want to have low accelerations, that means small dynamic amplification factors, we do a base isolation. So therefore, I would like to give here just a few examples to have some understanding. I would like to discuss here wind and water waves, and I would like to discuss earthquakes. If you have wind load, gust, or water waves in reservoirs, we have very low frequencies. So therefore, we are more in this range. That means we have no dynamic effects. Therefore, these loads could be treated as static load, but still time dependent, but it gives no inertia effect. On the other hand, for most earthquake effects, we are in this range here, unfortunately, which covers basically this resonance effect where we have amplifications. Okay, in most structural problems, we are in this range where we have some dynamic amplification effects. And I would show a few examples here, which discusses excitation frequencies and eigen frequencies of structures. And I'm giving here only some approximative values. I would like to say characteristic excitation frequencies, F, are, for example, for wind gusts. We have done quite a lot on that. Wind gusts are frequencies of 0.1 hertz. And if we have an eigen frequency of a structure of 10 hertz, the frequency ratio would be 0.01. That means, we would be, for wind, we would be somewhere here. Wind action on structures basically can be dealt with static analysis. Secondly, if we look in surface waves in lakes and reservoirs, which is dealing with dams, also the water waves are much smaller than 0.1 hertz. Again, water waves in a reservoir, the effects of water waves on the dynamic response of dams is negligible because, as I said, the frequency ratio is also here. We have no dynamic amplification factor. So water waves in a reservoir, also they are time dependent. They will not cause a dynamic response of the dam. The response is purely a static one. And if you look earthquake accelerations, the typical frequencies for earthquake accelerations are about 2 to 5 or 10 hertz. And if you look in this frequency range, this is also the frequency range of many structures, including concrete dams and also some, let me say, moderate embankment dams with moderate heights. We are in this range, 2 to 5 hertz. So therefore, in this scale, if you would do this, look into a frequency of structure, we would basically be in an earthquake case. In this case, in this amplification range, which shows that the earthquake case is basically, from a dynamic point of view, is an important one. Now, let me say a few words about what are some characteristic or approximate eigen frequencies of structures. The eigen frequency of a structure is F, which is different from the excitation frequency. That is this is the external load. If you have buildings, low-rise buildings, and most bridges are in the range of 2 to 10 hertz, that means are in the range of earthquake acceleration. High-rise buildings and very long-span bridges may have eigen frequencies of less than 1 hertz. So therefore, we may move already to smaller accelerations. Okay, if we frequency here is much less. Excitation frequency 2 to 5 hertz divided by 1 hertz gives the frequency ratio of 2 to 5. And if we look in this diagram, 2 to 5, look at this comes here, the dynamic amplification factor is very small, so the acceleration, let me say, which acts on a structure will be, the relative acceleration will become quite small. And if we look for large concrete dams, again, the frequency ratio, I give one example when on the 250 meters high arch dam has an eigenfrequency of about 1.5 hertz. For smaller dams, we may have frequencies up to 8 or 10 hertz. And we see this is in a range of the earthquake frequency. That means for large concrete dams, dynamic effects, earthquake effects are quite important. Now, the last case is reservoirs of storage dams, or also long penstocks that are pressure waves in penstocks or pipes, depending on the length of this penstock. If it is more than 1 or 2 kilometers long, the eigenfrequency of the oscillating water in penstocks and also in the big reservoirs is much smaller than 0.1 hertz. Okay, what does it mean? If you have a frequency of much smaller than 0.1 hertz, and we have, for example, a dam with a frequency of about 8 hertz, we will get here a ratio of 0.01 or even smaller. And if you look again here in this diagram, we can say waterways in a reservoir create no dynamic response in the dam. It does not mobilize any inertia forces, but we could say the whole analysis could be done for waterways, same as wind, as a static analysis. So we do not need, let me say, complicated dynamic analysis. And as you can see here, the damping ratio, which I would like to mention, the damping ratio here doesn't play any role. It is unimportant. The damping is unimportant. Similarly here, if you have base isolation, the damping ratio also has almost negligible effect, whereas in a range of resonance, the damping ratio plays a very large role. Therefore, let me say, if you do a dynamic response, if you use small damping ratio or large damping ratio, the possible maximum amplification will vary a lot. So therefore, for concrete dams, the selection of a damping ratio is a very important parameter. And if somebody wants, and some engineers are doing that, they want to have a small dynamic response, they choose large damping ratios, which is, I would say, just for the sake to get a small dynamic response. But this is, of course, not proper. Therefore, as I pointed out, in the Swiss dam safety regulation for concrete dams, the Swiss government specifies a damping ratio of 5%. Not, there would be a peak maybe here. Not that some people use 10, 15, 20% and can reduce the dynamic response very substantially by 50% or more. So therefore, the damping ratio is a very important factor in any dynamic analysis. So let me give here the examples, 2 examples, and the examples are where I discuss this frequency ratio of excitation frequency divided by eigenfrequency of a structure. So if we look wind load on buildings, we have here 0.1 Hertz, 0.1 divided by building eigenfrequency, which may be 2 to 10, is given here 2 to 5 Hertz. So that gives us a ratio of frequency ratio of 0.02 to 0.05. And as I mentioned here, 0.02, here is 1, so we would be in this range. So as I mentioned already, wind effects on structures, on dams, you know, also wind is, people think is highly fluctuating. It does not create any amplification, dynamic amplification in any dam and in most type of structures. The second example I'm doing here, I would like to show here, is earthquake on dams. I mentioned already earthquake excitation frequency is 2 to 5 Hertz. Is this here excitation frequency divided by the eigenfrequency, the lowest eigenfrequency of large concrete dams, which is in a range of 1.5 to 8. So if we do this ratio, we see this gives a bandwidth of about 0.25 to 3.3. And if we go back in this diagram, 0.25, okay, we are somehow here to 3.3, we come actually to a big range. So we can have, for quite a few dams, we may have large amplification effects. Okay, so basically, the understanding of a dynamic amplification factor allows you actually to give already, to make some qualitative statements on the dynamic response of the dam. For example, if you have a big embankment dams like Terry Dam, it may have an eigenfrequency only of about 1 or 1.5 Hertz. So therefore, we would basically be in a range of 2 or 3. So the dynamic response on the crest, you know, will not be amplified much. It could even be de-amplified. Whereas, on the other hand, if you have a dam, a concrete dam, which an eigenfrequency of 2 Hertz, we may be in a kind of a resonance range. So therefore, dynamic effects may play an important role. So therefore, this diagram, I must say, is very useful. It helps you to make, let me say, a qualitative assessment of all types of structures which you may encounter, and also on any types of applied dynamic loads. So this single degree of freedom oscillator, I must say, to understand this single degree of freedom oscillator is very essential in understanding any dynamic problem. So I would recommend you, maybe if it has been a little fast, to have a look into that at home. Now, if we look in one case, this is Cascio Dam. I think I've shown it already once, and I would also like to point out that some of the examples I'm showing repeatedly, simply due to the fact that there is not too much information available which on observed behavior of dams during strong earthquakes. So therefore, so please do not be disturbed to see some of the photos repeatedly. But anyway, this is a Cascio Dam, is a gravity dam, is about 40 meters high, and It was subjected to quite a strong earthquake, moment magnitude 6.7. And what has been recorded here, among others, is the water level in a reservoir at the dam. And if we look here, this here is now a water level in a reservoir just at the dam. And we see due to this strong earthquake, the peak ground acceleration was about 50% of gravity. We have an oscillation, which is a damped vibration. It's a free vibration, basically, of a reservoir. So the reservoir shown here is basically oscillating here in this direction. So therefore, it gives here some waves in the reservoir. But the wave height, as you can see here, due to this quite strong earthquake, is quite small. It is only 6 centimeters here up and 4 centimeters down. So the wave height is a maximum minus minimum is 10 centimeters. So the wave height is 10 centimeters, is quite small. But what you can see here, this is a measurement. It's a free vibration. It is a measurement like from a single degree of freedom oscillator, from a damped single degree of freedom oscillator. And you can see here that this reservoir is oscillating. The scale here is 2. This is 2 hours. You can even measure after 4 hours, 5 hours. You can still measure some small amplitudes. Of course, then if it becomes very small, it is superimposed with wind-induced vibrations. So the time scale here is hours. And if we do a frequency analysis of this response, we will get a curve like that, and which shows here the eigenfrequency in this range, or the natural, here is given not the frequency, is the natural period in minutes. And the minutes here, which are given, is about 6.5 minutes, which is 390 seconds. So the duration, the natural period of vibration of this of this reservoir is very long, is 390 seconds. And the eigenfrequency of this dam then is 1 divided by the period is 0.0026 hertz. And similarly, we can see from this free vibration, the damping ratio of a reservoir is quite small. It's only 2%. Now, if we have the frequency of a reservoir, which is the eigenfrequency of a reservoir. Now the question is, does this wave, we see this is a dynamic wave height, gives a dynamic water load on the dam. Does that create a dynamic response in this gravity dam? Okay, that is a question. We have a dynamic water load here with a frequency ratio, if I go back here, of 0.026, that means very small value. So if I go back here, the eigenfrequency of this gravity dam is quite high. I would say it's in the order of 5 to 10 hertz. So if we use now the ratio 0.0026 divided by 10 gives 0.00026. And if we go back, that means it gives a value which is close to 0. And if we see here, close to 0, we are here. So therefore, we can conclude from this simple diagram that the water wave caused by the earthquake in a reservoir has no dynamic effect on the dam itself, and that the time-dependent water pressure can be calculated by a simple static analysis. Similarly, I must say, if I go back, if we have a very long penstock here, for example, or let me say a very long penstock of more than 2 kilometers, we also get very low frequency of the pressure fluctuations in a penstock, and therefore the dynamic amplification on the dam or on any structure there will be a static one. The penstocks, and I think I will give once a small presentation on that, on the hydrodynamic actions in penstocks. The penstocks, which are this range where we can have some amplification, are very short penstocks with frequencies, eigenfrequencies also in the range of the earthquake eigenfrequencies. So only penstocks, I would say, with a length of less than 100 meters, also will experience amplified dynamic pressures. So that is basically what I wanted to say about basic structural dynamics. And as I said, most of the dynamic problems, just to conclude, most of the dynamic problems can be assessed qualitatively by this diagram. So therefore, if you have dynamic problems, please do not forget this diagram, and it is very important to understand, let me say, this single degree of freedom oscillator. And as I've mentioned here, it is possible in a dynamic analysis to idealize as a first approximation the vibration of a concrete arch dam, complex building, arch bridge by an equivalent single degree, or what I call here generalized single degree of freedom oscillator. Of course, the stiffness K and C have to be calculated by some methods, the same with the applied with the mass which will be activated by the first mode of vibration. So that is basically these examples which I wanted to show, and I can conclude that for concrete dams, they are subjected to earthquakes, the dynamic response plays a very important role, and there are only some exceptional dams, for example, like very high embankment dams, where the dynamic amplification effects are not very important, may not be that important, and that the applicable acceleration is smaller than the applied acceleration. So that concludes this first introduction, which is the basics, let me say, on all, I would say, earthquake engineering. So let me come now to the main subject, and I will talk about the seismic design and performance criteria of large dams. I just have to ask, do you see the slide? Sorry, do you see the slide? Okay, so if I talk about the seismic design criteria and the safety criteria of large dams, I have to discuss first for what structures or what are the key structures to be looked at. And I'm looking here first at the dam body and the safety critical elements. And I would just like to explain here. We have a dam body here. Okay, we are interested in the safety of the dam body, and up to now, I must say, if seismic safety assessments have been done, people have focused on the dam body. Okay, we have a dam body. Secondly, we have a reservoir, oh, sorry, I have some typing error, and the reservoir slopes. And the reservoir slopes during strong earthquakes, you may have mass movements into the reservoir, and mass movements may create large impulse waves in the reservoir, especially if mass movements are large and if they are close to the dam. You see here there have been some, it's not really mass movement, it's a debris, it's more or less a debris flow, so it is not critical because the amount of the volume of this debris flows or slides is relatively small. It does not create any impulse waves. Okay, the next item which is important for dams are spillway gates. As we can see here, these are small gates. In Switzerland, usually we have small gates because the spillways are small. The spillways are small because the catchments are small, and we do not have the very high intensive rain like you have during the monsoon. And the fourth element, besides the dam body, reservoir, spillway, we have low-level outlets, or we can call them bottom outlets. I will just mention here once more, bottom outlets are compulsory for any dam in Switzerland. This is not the case for many other countries, but in Switzerland, the dam safety authorities and the dam safety codes, regulations require bottom outlets. And here I would just like to show a bottom outlet from a dam in Iran. Some people standing there and opening here the gates of his two outlets. And I just want to show a sequence of slides. Okay, you see here they opened, and they are still opening, and it took some time, as you can see here, that in this reservoir there was a lot of sedimentation, so therefore if this low-level outlet is covered by sediments, it may be difficult actually not only to open the gates, but also basically to use them. Okay, what is a matter, as you can really see very nicely from the water pressure, it is eventually pressed through these gates. Near the dam we have very fine silty material, and not gravel will be deposited further upstream, which is pressed through the gate. And it also shows, okay, sedimentation or landslides may be critical for the safety of dams because they may block the intakes of low-level outlets, or also intakes of some of, let me say, intermediate level or low-level spillway outlets. So it is important to have this bottom outlets, and you see here, then after this, let me say, plastic silty material has been pushed out. Eventually, this bottom outlet is working properly, and we see what is being released is highly sedimented water flow. So therefore, it is quite important. Basically, for us, it is important that the bottom outlet is used in an emergency case, and that it has to be operable at all time. Therefore, it has to be checked. The operation has to be checked at least once per year in our case. Okay, this is a standard practice for the safety assessment, annual safety assessment of dams in Switzerland. Of course, there are then environmental problems if you would dispatch so much sediment in a downstream part of a river, it would kill the fish. So in our case, in Switzerland, we will not allow to release this kind of sediment. So therefore, if you open that gate, it would be best to open this gate and to check it, for example, during the monsoon season. Okay, I mentioned already slopes. Slopes are also safety critical elements because, as you see here, this is a picture taken from a crest of Yipinghu Dam in China, and you can see just a few hundred meters away, less than half a kilometer, you had during the Wenchuan earthquake, you had quite a few mass movements into the reservoir. It looks like into the reservoir, but at the time of the earthquake, the reservoir was almost empty. So therefore, the mass movements into the reservoir have not caused, let me say, dangerous impulse waves, which would have harmed people or which would have overtopped the dam crest. So it was harmless. This is a picture after the earthquake when the reservoir was filled again. So, but what I want to show is that the reservoir rim here, the abutments also, we can have stability problems, and unfortunately, it is the case that the stability of these reservoirs and also the abutments have not been, let me say, included in the seismic safety evaluation of most dams. Now, just for your interest, maybe, when I talked about, let me say, slope stability, the most famous landslide which has occurred, which you may not have heard yet, is the Usoy landslide dam, creating the Lake Saras in Tajikistan in Central Asia. This dam, let me say, is not a man-made, is an earthquake-made. It's a natural dam. Has a height of 650 meters. You know, it's more than twice as high as the highest man-made dam. So the largest dam in the world is a natural dam, and this dam was created by a landslide which was triggered by an earthquake of magnitude 7.3 in 1911, and this dam still exists. I would just like to mention, okay, we see here basically big landslide occurred here from this side and covered this valley with about 2,500 million cubic meters, and you see here the crest of this dam is very irregular. It forms a very big dam which still exists today. There is, of course, some water seeping through the dam and causing some erosion, but this dam existed already for 110 years, and there are several plans somehow to make this dam safer and to install an alarm system. Such help has been provided by the Swiss government. Okay, we see here maybe better. This is basically this irregular dam crest, and this shows the area where this big rock and ice slide has occurred. It was also reported that this dam has settled already 90 meters since 1911. But the dam is still there, and it creates a reservoir of several billion cubic meters of water. So it is really a safety problem for people living downstream. So what I want to say is you can create during strong earthquakes in some mountainous region, like here in the Pamir Mountains, you can trigger very large mass movements. And of course, if you have large mass movements, if it would occur into a reservoir, and in this case, further up in the reservoir, some further potential landslides have been found. And if these landslides would also be triggered by an earthquake, for example, the impulse wave may then overtop and erode the top portion of the dam and release part of a reservoir or the whole reservoir. So it is quite dangerous. So what I wanted to say, for the safety assessment, we also have to look in the possibility of mass movements in a reservoir, and you know it from your incident in Chamoli in February, that if you have large landslides occurring even in a catchment area, and the material propagates along the river, it may cause complete destruction of certain types of hydraulic structures. Besides the dams and the safety relevant elements, we also have to look into the appurtenant structures. And the appurtenant structures here I consider as the buildings on the premises of a dam, for example. For each large dams, you have some office and some storage buildings and so on. The effect on the powerhouse, switch yard, desilting basin. Okay, in the Himalayas, you have big desilting basins with very high basins, penstocks, and equipment. So they satisfy different safety criteria, because if they fail, people living downstream will not be killed or will be harmed. Only people living in these buildings will be affected. So the consequences are not severe like in the case of failure of a dam. Now, this is just given an introduction where we must apply the different safety criteria. I want to say safety criteria must be applied not only to the dam body, which has been standard practice up to now. It must also be checked for spillway, for low level outlet, and also for the abutments at the dam site, and also the reservoir slopes, and even the slopes of some in the catchment, as the case in India has shown in February. So what are the critical issues? I would like to repeat here once more, because I feel it is quite essential here. The seismic hazard is a multi-hazard. Please, I must say, after my discussions, you must really recognize this. It is not only ground shaking, also ground shaking is the main issue addressed in earthquake regulations and guidelines, and also building codes. We can have, in a large dam project, we can have fault movement in the dam foundation or discontinuities in a dam foundation near major faults, which can be activated during strong earthquakes, causing, of course, structural distortions. We can have fault movements in a reservoir. They may cause water waste in a reservoir or loss of freeboard. This has been more of a rare case, but there are quite a few dams which are basically on faults or discontinuities which could move during strong earthquakes. Most of the faults, of course, have been declared as inactive, but with the time now, with the new information, several of the faults which have been declared as inactive today have been declared as active or potentially active. So it is quite difficult to, with this definition of active faults or inactive faults. And then I must say what has been underestimated up to now are mass movements, rock falls into the reservoir, but rock falls also at the dam abutments, which may block when intakes of, for example, low-level outlets or even of spillways, or they may block, of course, they have many effects on other types of structures, like in China, the Wenchuan earthquake of 2008 has shown that mass movements have created greater loss during this earthquake in the epicentral region than actually ground shaking. But these mass movements basically have been, I must say, ignored or have been assessed wrongly by geologists, for example. They have their own definitions of safety, which is different from what we talk about dam safety in our case. Okay, there are other site-specific and project-specific hazards, depending on some materials. If you have embankment dams made on sandy, silty material, we could have liquefaction and so on. So we can have some other issues, or we may have build-up of uplift pressures in some concrete structures. So this is quite important. If you do a seismic hazard assessment, you should take into account that these are multi-hazards. Okay, just to show that here, this is a Sekidrut dam in Iran, just after the earthquake. You can see here there's some water seeping through this joint here, and we have more water seeping here. So these are indications that there have been cracks here. This is just after the earthquake. There have been cracks in the dam propagating through the whole dam body from upstream to downstream, but the water level was relatively small. The low, just slightly above this discontinuity, so water is only seeping slowly through these cracks. Okay, we see here some of the cracks are quite large at the kink of the downstream face. Okay, as you can see here, these are locations of stress concentrations, which are basically critical locations. We see these cracks developed along concrete lift joints, which were here at about every 2 meters. At the surface, the cracks look quite dramatic, but this is only spalling off of concrete. On the surface, the crack width is only a few millimeters. Also at the upstream face, near a gate here, power intake, you can see there is quite some spalling off of concrete at the location of a crack. But as I said, the crack is not 20 centimeters thick. The crack finally is only a few millimeters. Okay, this is for concrete dams. I mentioned already for embankment dams, we also have cracks. Often they occur in longitudinal direction along the crest. The other issue which I mentioned also is the effect of faults. This is the Chichi earthquake in Taiwan, where a fault passed here through this Xikang Weir, and this fault had vertical offsets in a range of 5 meters, and it is clear that in this range, these two openings were completely destroyed. Since the reservoir was small, it was released here, but as you see here, there are about 20 gates which are used during monsoon. So therefore, during a monsoon region season, you release much more water than which was released through these two damaged openings. So it didn't cause further damage downstream of the dam. Also, the rock falls I mentioned, they may be very critical. Here is the rock fall effect on the powerhouse. This is an infill wall, and you can see here it looks like people shooting with artillery in these buildings, in this building, and the stones which fell down here basically penetrated completely this unreinforced infill wall. So rock falls may create at the abutments local damage to structures close to the dam site. Landslide or rock falls, of course, it doesn't need big masses. Let me say some boulders, a few hundred cubic meters are enough to overturn here this retaining wall. We see it has been overturned, and there has been some impact of a rock on this pier. It seems to be unreinforced. This is a photo from a runoff river power plant damaged by the Wenchuan earthquake in China in 2008. So this damage is not due to ground shaking, and this is also not due to ground shaking. It is at the dam site. It is due to rock falls. So rock falls are quite important. We see here there are some rocks. We don't see all, but you may be able to see here. We have here kind of crack here, shear type of crack, which is a result of the impact of a boulder of several cubic meters on this pier. Okay. So rock falls, this is not due to ground shaking. This is basically all rock fall damage. So as I mentioned, rock falls have been underestimated at many dam sites. So it is necessary also to have a close look at them, especially based on the experience from Wenchuan earthquake, where in the epicentral region, as I mentioned, more damage or more people were killed due to the effects of mass movements than due to buildings destroyed due to ground shaking. Or here, it also shows some landslides. Of course, if a landslide, they may also block here. This could be a type of landslide, which I have shown, which may damage parts of these concrete piers of river power plants. And this picture I'm also using to show. This here is the weir with gated spillway. If during the earthquake or after the earthquake, it is not possible to open the gates, they were closed here at the time of the earthquake, here is a power intake. If you are not able to open the gates after the earthquake, that can be hours or days after the earthquake, depending on the amount of water flowing into the reservoir and the size of the reservoir, you may have overtopping of this dam. So therefore, it is essential that after the earthquake, you are able to operate the gates. Okay, in this run-of-river power plants, in the case of dams, it must be able to open the spillways if you have gated spillways, and also the low-level outlets to lower the reservoir. I will show that. But here it was not possible. So if you cannot lower the reservoir, or if you cannot control the water level in the reservoir, it may create a safety problem on this dam, and depending on the overtopping, because run-of-river power plants are not very high, maybe 20, 30 meters or even less. If you have an overtopping of, let me say, 2 meters, it would create an increased water pressure, and the sliding stability when you have this overtopping may be less than what is required. So for this kind of small dams, if you have overtopping, it may have a detrimental effect on the sliding stability, on the static sliding stability of a dam after the earthquake. So the overtopping may create also a safety problem to this piers. Now, I mentioned already what are the failure modes of, let me say, of this run-of-river power plants if you are not able to control the reservoir. Now, if we look into embankment dams, what can happen during strong earthquakes to embankment dams, or rockfill dams are a type of embankment dams. There are basically 2 modes which you have to check, I must say, for all embankment dams, and that is now for the dam body. Basically, you have to check overtopping. I've shown that before. Overtopping of a dam crest. Overtopping of a dam crest can be caused due to settlement. Settlement of the dam crest. That means compaction of the dam due to ground shaking. There was one dam in the Philippines which was shaken strongly during a strong earthquake in 1990, which settled. It was reported almost 2.8 meters. So basically due to compaction, you can have quite some substantial settlement, and if there is not sufficient freeboard, the dam could overtop just after the earthquake, depending on the water level in the reservoir. We can have slope movements at the crest due to ground shaking. That could be a stability problem similar to slope stability. If you look into a dynamic stability, if you have strong earthquakes, we can define moving masses which have safety factors of less than 1. And if the safety factor is less than 1, these masses will move. And these moving masses may create a loss of maybe equivalent to a settlement. Number 3, we can have impulse waves. Sorry, I have to take some tea. Number 3, we may have impulse waves in the reservoir due to mass movements. I've shown already I've mentioned this already a couple of times, and of course for impulse waves, it is important. Those are critical, which have a great mass, which fall from greater depth at great velocity, and those which are close to the dam sites. Mass movements tens of kilometers away from a dam site will not have a critical effect on large reservoirs. And number 4, we can have mechanical failure of gates of spillways and bottom outlets due to strong ground shaking, that they are damaged. So if they are damaged, as I've shown, or if the power supply doesn't work, as I've shown before, this will lead to overtopping. And the second mode, so what do we do? How do we control? And what do we provide as designer? Based on the analysis, we have to provide sufficient freeboard that the reservoir cannot overtop, or that the freeboard is enough that impulse waves in reservoirs cannot overtop the dam crest. The second mode, which has to be considered in all dams, is internal erosion, which is a very, let me say, frequent failure mode. There could be slope movements at the crest due to ground shaking, causing offset of filter. We know internal erosion is almost, can be excluded if the proper filters are provided in embankment dams. If you have no filters, then such dams are prone to failure, much more prone to failure. Sorry. And we can have a case if we have a dam on a fault, if you have fault movement, of course also a filter, the offset may pass through the filter and may offset the filter. And if a filter is offset and may no longer work, then internal erosion may start. Now, what are the seismic design criteria? We consider here, let me say, different types. I have shown this, but I will discuss it here in a greater detail. We have a dam body and the safety relevant or safety critical elements, which are gated spillway and bottom outlet. In addition, these are also some critical slopes which have to be added there. We consider 2 levels of earthquakes in the design. The first one is the operating basis earthquake, which is the current state of eigen. We consider 2 levels of earthquake, the operating basis earthquake with ground motion parameters determined for return periods of 145 years. If a probabilistic seismic hazard analysis is considered, you can use we propose that as a guideline, but this is not a fixed value. Therefore, I've written here it is negotiable with the dam owner. In some countries, we have seen in Iran, people like to use for the OB 500 years. In Germany, I think it's 250 years. In Australia, it may be 1,000 years. Okay, so this value can be changed, but we should say this is a kind of a guideline which would represent a probability of exceedance of 50% in 100 years, which would give a return period of 145 years. The second earthquake, which is more important, is the safety evaluation earthquake. And if we do a probabilistic seismic hazard analysis, the ground motion parameters should be for 10,000 years. This is for, let me say, high consequence dams. There are lower return periods for medium consequence dams and low consequence dams. It is clear if a dam has no consequences, you do not have to use the seismic hazard for 10,000 years return period. But this is a high-cold guideline, and we say this here is basically non-negotiable. But we have seen, of course, some countries are using different concepts. In Turkey, they use 2,475 years. And in some other countries or some regions, people argue on lower return periods, especially when the seismicity is very high. If you look in the Himalayas, I would say the peak ground acceleration, if you may use that as a characteristic value for an earthquake with a return period of 5,000 years, is about the same as the peak ground acceleration caused by an earthquake with a return period of 10,000 years, because this will become already very strong earthquakes with magnitudes in the order of 8. So therefore, if you use 5,000 years or 10,000 years, there is no big difference in the seismic hazards, in the peak ground acceleration or the response spectra. The main effect would be, for example, in the duration of strong ground shaking, because if you have stronger earthquakes, the fractured length of a fault will be much longer. And then you have to look into appurtenant structures. I mentioned already powerhouse, transmission towers, desilting basins, and so on and so on. Here you could use the design guidelines which are used for buildings. If you do not have specific codes, but it is clear if you have a thermal power plant on a surface, or a thermal power plant, or a hydro power plant, the powerhouse of a hydro plant, you do not need higher safety factors for the hydropower plant, for the powerhouse of the hydropower plant, than for the powerhouse of the thermal power plant. And you could use the similar design guidelines if you do not have specific guidelines. And basically the building codes are based on return periods of 475 years. In the US, it is 2,475 years, multiplied with a factor. Also, for temporary structures, cofferdams, river diversions, and critical construction stages, you must take into account some level of earthquake. It is like with a diversion flood. If your diversion flood has a return period of 100 years, I must say it would be reasonable to use a return period for cofferdams, river diversions, also in the range of 100 years, similar as a diversion flood. Okay, so you should take that into account. Now, based on what I have just shown in a previous slide, we have different types of earthquakes. We have, for the dam, we have two levels of earthquakes. We have the operating basis earthquake, and we have the safety evaluation earthquake. Now, in addition, we have the design basis earthquake used for appurtenant structure, that means powerhouse, desander, and so on. And we have a construction level earthquake. So we have four types of earthquakes to be used in the seismic design and analysis of dams. And for the safety evaluation earthquake, we can use two methods for determining the ground motion parameters of the safety evaluation earthquake. It can be done by what I would call worst case earthquake scenario, which is also called maximum credible earthquake, which is the earthquake scenario which may create the strongest ground shaking at the dam site. This is a deterministic analysis because it is based on an earthquake scenario. Secondly, we can use a probabilistic seismic hazard analysis and to determine the parameters of a maximum design earthquake, which would be related to a return period of 10,000 years for a high consequence dam. So if this is purely the, let me say, types of earthquakes, we have basically when 5 for the safety evaluation earthquake, we would use the maximum of these 2 if both a deterministic and probabilistic seismic hazard analysis have been carried out. So we have basically 4 types of earthquakes here. Now it comes to a question, what happens with reservoir triggered seismicity, if that is possible. We just had a workshop, let me say, or a symposium for the 60th anniversary of the Brazilian Dam Society, just about 10 days ago. And there were several cases presented where dams have experienced reservoir triggered seismicity. Actually, quite a few of the Brazilian dams have been experienced reservoir triggered seismicity. So therefore, the question is, what shall we do with reservoir triggered seismicity in a concept of these, let me say, design earthquakes, which are listed here with 4 types. It could be that the largest, let me say, reservoir triggered seismicity earthquake is larger. It gives ground motions which are larger than those of the design basis earthquake. If that is the case, or also the operating basis earthquake, if the parameters of the largest reservoir triggered seismic event are larger than those of dB and OB obtained from a probabilistic analysis, then these ground motion parameters of the RTS shall be used in this case and in this case. Sorry. Okay, that is the effect of design basis earthquake of the reservoir triggered seismicity. Reservoir triggered seismicity has no effect on the safety evaluation earthquake. So therefore, for the safety of the dam, basically the reservoir triggered seismic events are not relevant, but they are relevant, may be relevant for the design basis earthquake, operating basis earthquake, because powerhouse may be damaged due to reservoir triggered seismicity, but the dam is still safe. And also we may have some damage, some smaller damage, which have to be checked in a case of reservoir triggered seismicity for the operating basis earthquake. But reservoir triggered seismicity, I will discuss it separately, is also based on some scenario. We define some scenario like the worst case scenario here, the maximum, let me say, reservoir triggered earthquake, but we are not, let me say, this is quite hypothetical, and it includes very large uncertainties. So therefore, it is not really possible to predict the occurrence of reservoir-triggered seismicity. There's only some probability, and it is not possible basically to include them in some probabilistic seismic hazard analysis, because these are specific events which occur mostly during the first few years of operation or during impounding of a reservoir. Now, where do we have to apply the seismic design criteria, which I just mentioned? I would like to just show this slide and one more, and then we will stop for a break. Where do we have to apply the seismic design criteria? I mentioned this, just a repetition, that we consider 2 earthquake levels are considered for the following structure. Now I'm talking about high consequence dams. We consider 2 earthquakes, operating basis earthquake and safety evaluation earthquake for the dam body. And it is important, I would like to point out, when we talk about the dam body, it must include saddle dams. If you have saddle dams where the reservoir can be released, as the case has shown in Laos about 3 years ago, then it is obvious that the saddle dams must have exactly the same safety, seismic safety criteria or the safety criteria than the dam body of the main dam. So please don't forget that. Many dams have several saddle dams, especially dams in relatively flat areas. I think in the Panama Canal, it was mentioned, I was involved, I think there is one main dam, and there are up to about 30 saddle dams there. Some, of course, are small, where the reservoir could not be released, but some are large ones. So these saddle dams, also, they may be smaller, and the engineer may only draw attention to the main dam. You must consider properly saddle dams. It's important. Number 2, we have to apply the seismic design and safety criteria to safety critical elements. These are spillways, low-level outlets. Low-level outlets, okay, what are they? They could also be called bottom outlet, irrigation outlets, flushing outlets. Okay, they have different names, but they are basically low-level outlets. And they must be operable after an earthquake, as I mentioned already in the previous slide. When we have to look in the dam abutments, the abutment stability is, of course, of great concern for arch dams, because arch dams are very vulnerable to foundation movements, to abutment movements. They may only accept a few millimeters or a few centimeters at most, without creating cracks in this rigid dam body. Number 4, the seismic design and safety criteria must also apply to reservoir slopes, and that means rock slides or landslides may block intakes or safety critical elements, or may create important impulse waves in reservoirs. Okay, that are the direct reservoir slopes, but as you have seen in India now in February, you must also go beyond the reservoir slopes and to look into the formation of some mass movements in the catchment area if these rock slides or debris flow will propagate into small reservoirs, especially. So we consider for these elements 2 levels of earthquakes, and as I pointed out, in the old days, people only looked into dam body. Now you have to look into a seismic safety in a more comprehensive way. I must say, saddle dams is just one point. It should be obvious that they should have the same safety criteria, but we have to look in safety critical elements, in dam abutments, and we have to look into reservoir slopes. So with that, I would like to stop here with first presentation, and I think we have a break for 2 hours, and we will continue in at 3 o'clock Indian time. So if you have some questions, maybe. So we would like to stop here for the 2-hour lunch break.
See you all for the next part of the session at 1500 hour IST.
Okay. If you have some question, you can also put it on the chat, in the chat box.
Or the participant may ask directly if they have any questions or queries.
Okay, so we will do it afterwards in the afternoon. So we break here. No questions.
Yeah, are you able to hear?
Yes, we can.
Yeah, this is Dr. I.D. Gupta. I have a question. If you are not going to cover that in the subsequent lectures, otherwise you can reply. You have indicated 2 levels of earthquakes, that is SEE and the OBE for the dam safety. Now, what are the difference in the methods of analysis and the safety criteria to be adopted for these 2 levels of earthquakes?
Okay, thank you for this question. It's a good question. I will discuss it in a subsequent slides then.
Okay.
I will also discuss about the methods of analysis.
Okay, that's okay.
Yeah.
Sir, I am Vivek Tripathi from Central Water Commission. I want to ask what is difference between OB and DB, because appurtenant structures we are designing for DB, which is return period is 475, and OB we are designing our dam and gated spillway etc. for operating basis earthquake in 145. So why it is different?
Well, I try to explain it how we can, let me say, clearly distinguish with different types of earthquakes. I know that some people like to mix OBE with DBE. So therefore, I have used here in my presentation, let me say, the definition we used in ICOLD. But I'm aware that in some countries, people do not talk about OBE, but they also talk about DBE. But it could be, as I mentioned, also in Iran, for example, the return period of the OBE is taken as 475 years, which is also the return period which is used for appurtenant structures, where we call also DBE. So therefore, sometimes there is a mismatch between these earthquakes. But as I've said, the OBE can be specified by the dam owner. It is not a universal value. We recommend a minimum value of 145 years. So it could be that you say for the spillways, you use an OBE with a return period of 145 years. And for the dam body, you use the OBE of 475 years. You could use the OBE specific to your structure of your power plant or of your project.
Okay.
But we would still call it OBE, but you would just use different return periods for different elements of your project.
So what is difference? Means what is only difference between OBE and DBE? You can use DBE also.
Yeah, well, if you use DBE, it may be also a cost problem. Okay, I would say it would not be a problem, in my opinion, for embankment dams. But for some concrete dams, it may be a problem if you use a long return period, 475 years, which is from building codes. And in building codes, you allow inelastic behavior, let me say plastic hinges in columns and beams. But in a dam safety, we specify that under the OBE, you should not have any structural damage, only minor damage, which is easily repairable. So if you use 475 years for, let me say, a big arch dam, you may get into problems. That means you may have tensile stresses, high dynamic tensile stresses, which may cause cracking. But we request for the OBE that we do not have, let me say, significant cracking or only minor cracking. So therefore, you will get already into some problems. But you can do it. It is not forbidden. You can use it 475 years. But we say 145 years is a minimum which represents a probability of 50% of probability of exceedance of 50% during the lifespan of 100 years. So therefore, we get this 140 years.
Because
But
this
475 years, it comes from the buildings. In the buildings where people have introduced it, is a probability of exceedance of 10% in 50 years. Let me say more related on building structures.
Because in India, we are never using 145 return period. We are using DB 475 return period only.
Yeah, okay. But it is important that you use the proper definition, you know, for the dam body and for the safety critical elements. We have the two levels of earthquakes, what I call their OBE and SEE. And for the other types of structures, appurtenant structures, we say you use at least the specifications given in seismic building codes. And in building codes, people refer to the design earthquake as design basis earthquake, and which is 475 years. But for appurtenant structures, you may have your own code. So you can specify their additional requirements, which are not the subject of this dam safety discussion. This is more buildings, well, for power plants where you need higher importance factors. Longer return periods are there considered in seismic codes by specifying importance factors for different types of structures. For example, powerhouse, we would say equipment's importance factor of 2.5. Of office buildings, is also where, if we use a seismic design code, we use an importance factor of 1.1, 1.0 or something like that. So you can, if you do the building codes with dBE, you would also associate those with importance factors if you do seismic design of structures.
Professor Villain, in India, we are using the SEE with 2,500 return periods. And if we go to 10,000 year, the ground motion will be much higher compared to 2,500 years. Now, it all depends on that whether it is 2,500 or 10,000, how you utilize it in the analysis and what criteria you satisfy in terms of the stresses or deformations or any other parameter. Because ground motion alone doesn't carry any meaning unless it is compatible with the safety criteria to be satisfied. And we are not very clear that what the dynamic stresses should be allowed in case of, say, concrete dams or settlements in case of rockfill dams, how to calculate, what method to use. So that is the whole problem, because that's why I asked the earlier question that what analysis and what safety criteria should be satisfied. 145 may be okay if our safety criteria are very stringent in terms of stresses, because how to define that no damage? That is the main issue.
Yes. Okay, maybe your first no damage basically means yes, allow the stresses. That is like in structural analysis, serviceability limit states, which are, for example, crack control in reinforced concrete. Now, in a safety evaluation earthquake, we specify that we have no uncontrolled release of a reservoir. So therefore, for the ultimate safety of the dam, it is a safety evaluation earthquake which is relevant, whereas the operating basis earthquake is relevant for the dam owners because they know if this earthquake occurs, they do not have to expect important damage, and they do not have to provide, let me say, a budget for repair of such damage. If you increase this return period, of course, you should make your dam safer, or it may change the dam geometry slightly when this includes the cost of a dam, but when during the operation phase, the probability that the strong earthquake occurs is much smaller, and therefore the budget then for maintenance or for repair, you could think about that, would be lesser during the operation phase. Therefore, I said this is more an economic criteria of the operating basis earthquake, and it can be, let me say, determined by the dam owner. But we basically say we think that 145 years is okay, but if somebody feels, the dam owner, he wants to have more safety for the OBE, it has no effect on the safety evaluation earthquake, then we can have that, he can do that. This is absolute okay. Now with a return period of 2,400 or 500 years, like in the US, I would say if I look into India, okay, you have the high seismic zones in the Himalayas, foothill of Himalayas, and so on. So therefore, maybe with a return period of 2,500 years, you will get quite strong earthquakes. But in the, let me say, subcontinent, on a stable subcontinent, your seismicity is relatively low, unfrequent. You may have some stronger earthquakes. Therefore, in that region, to have these intraplate earthquakes and so on, I would still say 10,000 years would be better. You should
Yeah,
use
yeah.
the 10,000 years, but in the Himalayas, I understand also in Turkey, people use 2,500, but 2,500, it doesn't come from